Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us begin solving this step by step. Step 1. Formation of compound. A phenylacetylene, pH CCH, is treated with 9H2, a strong base, to deprotonate the terminal alkyne, generating the acetylide anion pH Cc. This nucleophile then undergoes SN2 alkylation with cyclohexyl tosylate, TSO, cyclohexyl, to give pH CC-CY, i.e., phenyl cyclohexyl acetylene, internal alkyne. Compound A is equal to pH CC-CY. Step 2. Formation of compound B. The internal alkyne pH CC-CY is subjected to dissolving metal reduction conditions, Na NH3 liquid. This is a Birch-type reduction of an alkyne, which gives the trans-E alkene via anti-addition of 2 hydrogen atoms. Product B is equal to trans-PHCH is equal to CHCY, E1 phenyl 2 cyclohexylethylene, a trans-desubstituted alkene with pH and CY on opposite sides. Step 3. Formation of compound C. The transalkene B is treated with MCPBA, metachloroperoxybenzoic acid, a standard peracid epoxidation reagent. Peracid epoxidation of alkenes proceeds with SYN addition of the oxygen across the double bond, retaining the relative stereochemistry of the alkene. Since B is trans, pH and CY on opposite faces of the double bond, the resulting epoxide will have pH and CY on opposite faces, trans relationship in the epoxide ring. This corresponds to the trans epoxide shown in option B, where the phenyl and cyclohexyl groups are on opposite sides of the epoxide plane with the depicted H atoms on the same side. Why option A fails? Option A shows a cis-epoxide, pH and CY on the same face with oxygen on the bottom, which would arise from epoxidation of a cis alkene. The dissolving metal reduction gives transalkene, not cis. Why option C fails? CY would require oxidative cleavage or a different reaction pathway, not simple epoxidation. Why option D fails? pH CH2 CO-CY is a ketone product from rearrangement hydration, not direct epoxidation. Therefore, the correct answer is B. Therefore, the correct answer is option B.